Hello, everyone. This lesson is going to be in our chapter 6 from our textbook, and the title of it is the normal distribution. Before we kind of get into the sections of the chapter, there's some things that I kind of want to front load to you about the normal distribution. So we're just going to call this the intro to our chapter here. So the first thing is we need to know that the normal distribution has two parameters. We call it the mean, which uses the Greek letter mu, and the standard deviation, called sigma. Or you'll also see, if you were to look online and you look at different things or different textbooks, what they will also put in there, where it's publishers or people lecturing, you'll see the standard deviation will also use, instead of writing out the word standard deviation, it'll say SD. Okay, that's another way you might see it. Okay, so first thing is you have a notation that I want to go over in our textbook, and it says N has a little squiggly like a tilde, and an N here, XN, and then has mu and standard deviation. So what does this mean? This means we say that X has a normal distribution with the mean, or mu, and standard deviation sigma. Now, what you're going to actually see is, instead of it being mu and sigma, those will probably be values the majority of the time. Your X is just your variable. So talking about your variable, could be X or Y or any variable it really insists on being. And then the N talks about has a normal distribution. So what is a normal distribution? It has what we call like a symmetrical curve, like it's a bell curve, right? You see this in a lot of statistics. You might see it in some data that they show you, kind of manipulate it a little bit. But this is what we're looking at. We're looking at our bell curves. All right, this is what we mean by has a normal distribution. Okay, in the normal distribution, there's a few things that you need to know. So I'm just kind of highlighted parts. The first thing is the mean is the same as the median. And that's because it's symmetric about the mean. Because I'll just have it of the symmetry about mu. Right? A couple more things. If we change, so a change in the standard deviation makes the curve taller or flatter, depending on what happens at standard deviation. The last thing before we move into our first section, a change in the average, the mu, causes the curve to shift left or right. It depends on what the average actually is. That should be say shift. All right, so now we're ready to move into our first section here. So 6.1, the standard normal distribution. We have two sections from our text. to cover in this chapter. So first, let's define something we're going to talk about a whole lot, and that's our z-score. So a z-score, I'll highlight it for you so this is going to be a little bit more important here with being a definition. So a z-score is measured by how many standard deviations a value is away from the mean. And to talk a little bit more about it, let me just do this. So it'll go above the mean, and in our visual approach, it means that it goes to the right. And if it goes to the right, it has positive values. So if it's above, that's one option. So if it goes above, it'll be to the right side of that normal distribution curve. That means your z-score, your z-value will all have positive values. So between something greater than 0 all the way, greater than 0. Then we can be below. If we're below, that means we're to the left. And that means that we're going to have negative values. The last thing is, since you could be above the mean or below the mean, we're talking about positive and negative. What happens if we don't have either one? What's our third option? Or 0. And that's when our value, our x, equals the mean. So x is the same as mu. If we're going to try to use some math terminology there. Now, we're also going to say if x is a normal distribution with your mu and standard deviation, then the z-score is, and this is how we're going to use this equation a whole lot. Z equals x minus mu over the standard deviation, over sigma. You hear me say standard deviation more than you hear me say sigma, so I'll try to get in the habit of using the same terminologies. One thing I want you to know before we solve anything is this is going to be incredibly important, first off. You use this a whole lot. And there's one thing I want you to know about this. Oops, sorry. We are going to round z-scores to the nearest hundredth. Okay, and when we round nearest hundredth, that's 2 decimal places. But this is also another big important spot here that we need to make sure we remember. To the nearest hundredth is how we're going to round. So let's go ahead and go to our first example of the chapter. So example 1, what is the z-score of x when x equals 1 and x has a normal distribution 5, 6. So from this, you should identify a few things. To find the z-score, you think about our formula, which is in green right there. All right, so think about this right here. What do we have? We have z, we have an x, we have mu, which is our average, and we have sigma, which is standard deviation. So we have 4 variables. This asks for what is the z-score. So if we're wanting to know what the z-score is, that means we do not know this, which means we need all 3 of these. It says x is 1. You have 5. Remember, 5 is your mu, right? This thing listed first. And then 6 is your standard deviation, your sigma. So we have 1, 2, 3. We have all 3 of these. So we're going to take and substitute those in to there and simplify, and that's going to give us our z-score. So I'm going to say z equals x minus mu over standard deviation. And you're going to see that I write out just a general formula a whole lot. I think it's really good to continue to write it. That way it's just repetition, repetition. Do you need to on an assessment? Do you need to for your own benefit? Those are 2 different things. For the assessment, I will not require it. For your own benefit, I don't see why not add it. How much longer does it really take? Right? So that way you can at least get it ingrained, because the more you write it, the more repetition is just muscle memory at that point. So we're trying to find the z-score. So we have x is 1. We're going to substitute now. Your mu is 5, and your sigma is 6. We can keep going with this. If I simplify it, you're not going to need to simplify it, but I'm just going to show you. If I simplify it more, negative 2/3, or we can say negative 0.67. Now, why did I not keep carrying over? Because you know that negative 2/3 is 0.6 repeating. But remember what we have highlighted in this magenta color or pink, whatever, round to the nearest hundredth. So it's really negative 0.66, and we just keep going with this, right? But we need to round to here. So remember, you take this, and if it's 5 or more, you round here, right? What's the saying is 5 or more up the score, 4 or less, let it rest, I think I heard once. Stuck with me. So here is our z-score for when x is 1, x is normally distributed, your mu is 5, so your average is 5, and your standard deviation is 6. Okay, so this next example has a little bit more writing in it, so instead of you watching me write, I thought I'd give you time. So I'm going to go ahead and pause the video. I'm going to have you pause it and just keep, and write all this down. And then you can pause it how you want to throughout this problem to keep writing. You can leave the space now, or just write the beginning part, and we'll move from there. Okay, so I'm going to go ahead and pause this right now for you. Okay, so coming back means that you have now written all of this, or at least the top part here. You've at least written all this, so we can talk about the context. So it says some doctors believe that a person can lose 5 pounds on the average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. Let X be the amount of weight lost in pounds by a person in a month. Use a standard deviation of 2 pounds. So you say X is normally distributed, your average is 5, and your standard deviation is 2. You're going to fill in the blank. It's kind of like a beginner part of it. So A says, suppose a person lost 10 pounds in a month. So it says the z-score when X is 10 pounds is 2.5. So it wants us to verify this. So before we move any further, let's verify this. So how do we verify this? Well, we know that our X is 10, our average is 5, and our standard deviation is 2. So there's 3 of those variables that we need to find our z-score. So what we should do is, or what we're doing is, we're going to use that z-score formula to see after we put those 3 numbers in, these 3 that I've highlighted here, does the z-score become 2.5 or is it? So we're going to say z equals x minus mu over standard deviation. Our X is 10 here, right? Because you lost 10 pounds. And remember, well, why is it not negative 10 though? I don't understand. When you lose, it shouldn't be negative. We'll read this. Here's an important part here. X is the amount of weight lost in pounds by a person in a month. Okay, so that number is just how many you've lost. It doesn't actually become positive or negative there. So if you lost 0, then it'd be 0. right? Now, if you gained, this is where your negative values come in, right? But as long as you lose, they become positive. All right, now we have our mu, what's our average, which is 5. Standard deviation is 2. Again, you don't have to simplify it. If you do, you get 5 halves. You put that into a calculator, or if you know it off the top of your head, it's 2.5, which, hey, look, it checks out, right? We verified that z is 2.5. So the z-score tells you that x equals 10 is 2.5 standard deviations to the right of the mean, which is 5. Okay, so visually, this is what it is. It means that we're going to the right. We have a positive z value, correct? We said if it's to the right, it's positive values. And because our z is 2.5, that tells us our z is how many standard deviations away from the mean your x value is. And our mean is 5. Now let's look at B. B says, suppose a person gained 3 pounds, which is a negative weight loss, then z equals what? So let's find out what that is. So remember, if someone gained 3 pounds, x is negative 3. So z equals x minus mu over the standard deviation. So our x is negative 3. And then everything else stays the same. We still have the same distribution. Our mean is still 5, and our standard deviation is still 2. So minus 5 divided by 2. So we keep writing it out if you want to. Negative 8 over 2 is negative 4. So what does this tell us? Then z equals negative 4. This z-score tells you that x equals negative 3 is 4 standard deviations to the left. Why is it to the left? Because our z value is negative. And when we have a negative z value, we are now on the left side of that normal distribution curve. I'm going to move this up. We're going to lose some up there, but that's okay. We'll gain some space. So it says, suppose the random variables x and y have the following normal distribution. X is normally distributed, and then your mean is 5, and your standard deviation is 6. Y is normally distributed, your mean is 2, and your standard deviation is 1. If your x value is 17, then z is 2. All right, this wasn't really previously shown. In the textbook it was. I just used the same text, so I should have crossed this out here. So we're going to show this. Okay, what is z? Let's prove that z is 2. So if z is 2, I'm going to say, I'm working my x value, so z, I'm going to say sub x. That's the value that I'm working with. I'm looking at my x value. I still have, that one's supposed to happen, is x minus mu over my standard deviation. My x is 17. My mu is 5. And my standard deviation is 6. Remember, we are using this right here. That becomes 12 over 6, which is just 2. Boom, it says z is 2. Okay, we're good there. Now what happens with our z-score when it's y? So now we're going to say y minus mu over standard deviation. And now the only reason why I changed x to become y is because that's the variable we're using now. That variable is interchangeable. And our y now is 4. I guess I could do this. Let me just change this really fast. So here is what we're doing now. And then our y value is 4. So we have 4 minus, and our mu is 2, and our sigma is 1. We have 2 over 1, which is just 2. So that's weird. I have different x value and different y value. Well, what does that really say? Well, I mean, shoot, look at these. They're both 2. So how is this? So this is because they are both 2 standard deviations away from their respective means, right? Their means were different. Their standard deviations were different. So the x value is 2 standard deviations away from its mean, and the y value is 2 standard deviations away from its mean because they are different. So the z-score, what the z-score allows us to do it allows us to compare data that are scaled differently. That's what the z-score allows us to do. All right, there's next thing here that I want to show you. So what is this funky curve here? So I'm going to teach you about the empirical rule. It's also called 65, 95, 99, 7.7 rule. I'm not going to write that, but we're just going to call it the empirical rule. What that means is that all of your data that you have in a normal distribution curve, between the standard deviations from here to here, so one standard deviation away, 68% of your data lies within one standard deviation away from the mean, which is, you know, quite a bit. That's a little more than 2/3 of your data lie one standard deviation away. And as you get further and further, you're going to collect more data in there, right? So if I go here and I go 2 standard deviations away, between 2 standard deviations away, we have 95% of our data. And the last one that we talk about, and we talk about it lastly because look at the difference now. We have 99.7% of our data within 3 standard deviations away. At that point, what is really the whole idea of going any further than that? To get to that 0.3%? We do, we can, but this is where a majority of what we do lies, between 3 and -3. Let's get to our next example. Again, I have it typed up, so I'll allow you to pause this and then go ahead and write it. All right, so now that you've written it, let's talk about it. I'm going to read it. So this is from 1984 to 1985. The mean height of 15 to 18-year-old males from Chile was 172.36 centimeters, and the standard deviation was 6.34 centimeters. It says let y equal the height of 15 to 18-year-old males from 1984 to 1985. Then, and here's our key here. Y is normally distributed, and then we have a mean of 172.36 and a standard deviation of 6.34. The next little part says the mean height of 15 to 18-year-old males from Chile from 2009 to 2010 was 170 centimeters with a standard deviation of 6.28. Male heights are known to follow a normal distribution. Let X be the height of 15 to 18-year-olds, 15-year-old male from Chile in 2009 to 2010. And then now here's our next part. X is normally distributed, and your mean is 170, standard deviation 6.28. Find the z-scores for when X is 160.58 centimeters. I should make sure I get all of centimeters there. And Y is 162.85 centimeters. Interpret each z-score. What can you say about x equals 160.58 centimeters and y equals 162.85 centimeters as they compare to the respective means and standard deviations? So first, let's look at the first thing it asks. It asks for the z-scores. Let's start with x. It just gives it to us first. So we're going to say x equals 160.58. Trying to find my z-score, so z equals x minus mu over the standard deviation. Our x is 160.58 centimeters minus our average is 170 divided by our standard deviation, which is 6.28. Put all this into the calculator, just the way you see it, you should get negative 1.5. If you do not get negative 1.5, and you have what we have so far, it's probably a calculator error that you've done, so go back and look at it. Next, let's look at y. Y is 162.85. Everything, I forgot the 2. Everything we're having in yellow here, 162.85. So our z-score is still, instead of x, we're going to say y. Y minus mu over the standard deviation. Y is 162.85 minus 170 divided by 6.28. Oh, I'm sorry. They have different means and different standard deviations. See, I get ahead of myself sometimes. It's easy to do. These have changed. They're not the same distribution. So in yellow, we look up here, 172.36. And then over here it's 6.34. So 6.34 equals, you put that to the calculator and you get negative 1.5. We've done something again. It says interpret each z-score. Something else happened. What can you say about these two? Well, what we can say is between these two, both x and y deviate. Let me move a little bit over here. Deviate the same number of standard deviations away from their respective means. And in the same direction. Well, I thought they were the same direction. No, because they're not all, just because they have the same standard deviation away from the mean does not mean they're in the same direction. In this case, they're both negative 1.5. But if one was negative 1.5 and the other was positive 1.5, they would both still deviate the same number of standard deviations away from their respective means, but they would go in opposite directions, right? But because they're both identical and they're the same, then we can say they're also in the same direction. Okay, moving on to this next example here. So you go to pause it here, write this, and then I'll come back. Okay, so you might have noticed like, well, hey, did we just do this problem? We didn't do the problem, but what we're going to do is we're going to talk about if we were to continue this problem and extend it. All right, so still using the mean height of 15 to 18-year-old males from Chile during 1984 to 1985. Tells you it was normally distributed. And here is the important part right there. I'm kind of zoom in a little bit and we'll work our ways down. Okay, so it says about 68% of the y values lie between what two values? So think about our empirical rule. So where does 68% of these lie? They lie within one standard deviation away from the mean. So how do we do this? Well, first off, for A, our standard deviation, remember, is still 6.34. That does not change. Well, if you look at our mean, our mean is 1 point, oh gosh, I keep adding the decimal, I apologize. 172.36. So that's our middle of our curve. So if I go below 1 standard deviation, I'm going to subtract the standard deviation. That gives us 166.02 centimeters. All right, so I'm drawing my curve. There's my middle there, the 172.36. I'm trying to find what these values are to be 1 standard deviation away. So this 166.02 is this one right here, 166.02. Okay, now I need to find this one here. I'm trying to find this one. And we're at 172.36 plus 6.34. And that gives us 178.7 centimeters. So about 68% of the Y values lie between what two values? These values are 166.02 centimeters and 178.7 centimeters. The Z-scores are -1 and 1, respectively, right? Because they're both 1 standard deviation away from the mean. One's to the left, so it's negative. One is to the right, so it is positive. So now B, same standard deviation. But now, instead of us starting here in the middle, we're going to keep going. So now we need to go 1 more standard deviation away from here to be over here now. So now we're trying to find this line here, this vertical, which is 2 standard deviations away. So instead of starting at the mean, which is 172.36, we're going to start at our value, which is here, and that is 166.02. So 166.02 minus our standard deviation is 159.68 centimeters. And now to get to our upper bound, we're going this way now. We're going over here. So again, we're not using the mean, we're using this value, and we're going to add a standard deviation to it to get out here. And that value was 178.7. Where am I getting these from? Right here. These are the previous problem. And now I'm going to add standard deviation. And this gives us 185.04 centimeters. So about 95% of the Y values lie between what two values? These values are 159.68 centimeters and 185.04 centimeters. The Z-scores are -2 and 2, respectively. Right? 2 standard deviations to the left, 2 standard deviations to the right. All right, last one here. So we have these now. I'm just going to keep building to this graphic up here. I'm going to put this as our middle, so it's a different color here. Now we need to find out here, because we need the 99.7, which is 3 standard deviations away. So same thing. We still have the same standard deviation of 6.34. But instead of starting at 172.36 or 166.02, we're now starting at 159.68. That's going to be our first lower bound. So 159.68 minus 6.34. When we put this into the calculator, we get 153.34 centimeters. And that will take us to here, our third standard deviation to the left. Now we need to find over here. Remember, we already have this one, so we know this is a number over here. I'll stop writing so you can see it. So this is a certain value. And if I add the standard deviation to this, then I'll get my 3 standard deviations. So this number comes from right here. So we're 185.04 0.04 plus 6.34. And that gives us 191.38 centimeters. So what 99.7% of the y values lie between what two values? These values are 153.34 centimeters and 191.38 centimeters. The z-scores are -3 and +3. So now we have finished our example 4 and answered all of its questions. So now we have found all of those. All right, so this ends section 1 of the standard normal distribution. So now we're going to 6.2. 6.2, or section 2 of chapter 6, is entitled, and we'll go ahead and write this here. So 6-2 is using the normal distribution. All right, so now what exactly, everything I just talked about, what the heck are we going to do with it? So first off, here is kind of a vision when we talk about shaded regions. So notice how we said something like, you have negative values, you have positive z values. That's great. But now we're going to start using about the probability and actually using these z values to determine things. So first thing I want you to know is that the area under the curve is 1. Okay, what does that mean? That everything underneath that curve is the probability of it all happening. We're going to look at the average test score. We're going to look at the average weight loss. All of these different things that we're looking at, it encompasses every possibility underneath that curve. We might not look at every possibility, but if I was to add all of these values up in here, everything in here, this would all be equal to 1 because everything lies underneath the curve. So let's talk about that a little more. So if the area to the left is, let's say, 0.0228, then the area to the right is, well, think about it. If everything underneath that curve is 1, right? So let's draw the curve here. I could have used that one right above me. I'm gonna draw this. Maybe we can draw this a little bit bigger here. So I'm over here because I have a small value here. But if everything over here is 0.0228, that's everything over here. If I was to shade all of that, well, what's everything to the right? Well, if the whole thing equals 1, and I kind of take away this part, but the rest, if I add it, it's still 1 because it's a whole thing. Then what I'm going to say is I'm going to take 1 minus 0.0228. And this gives me 0.9772. So this area over here is 0.9772. Because it all adds to 1 underneath that curve. All right, so let's look at now a problem. This is going to be a little bit lengthier for sure. All right, so here's our first example of this section. So the final exam scores in a statistics class, of course, were normally distributed with a mean of 63, and standard deviation of 5. So here's our setup. Remember what this tells us. So here's part A. Part A says find the probability that a random selected student scored more than a 65 on the exam. So what is our X value here? So let me put this all in a different color so it kind of, you can see the problem is in blue and everything we're going to solve is going to be a different color. So our X represents a score on the final exam. Okay, and X is normally distributed because it says right here, normally distributed. Our mean is 63, standard deviation 5. 63, 5. Okay. Now here's what we have. Okay, well, that's fine. So what do we need to find first? What we need to find first is a z value. Okay, we need to find a z value first. What does that tell us? That tells us how many standard deviations away this x value is away from the mean. So what I want to do is let's actually draw this. Let's put it over here. So our mean is 63, and our x value, we said 65, because that's the score on the exam. We want scores more than 65, so we're shading more than 65, which is all out here. So this is where we are looking. So first, we want to find the z-score. And what the z-score is going to tell us is going to tell us how many standard deviations away from the mean that 65 is, but it's also going to tell us what percentage lies in that standard deviation, right? Because it's not always going to be a z-score of 1 or a z-score of 2. What happens when the z-scores are not nice whole numbers? So our z, x minus mu over the standard deviation, x is 65, our mu is 63, standard deviation is 5. That gives us 0.4. Great. Again, that tells us what the z-score is, which tells you that 65 is 0.4 standard deviations away from the mean of 63. What do we do with that now? Now we get to go to our chart. Some places and some textbooks or some lessons will have you use technology. Going old-fashioned, using the table. It's always handy. Doesn't require you to get a fancy calculator. So here's the table we're going to use. This is actually textbook that we use. Doesn't have the table in this textbook, but the same publisher and author uses a table in another textbook of statistics book that I've taught out of. So I just grabbed the table from that textbook. So here is the Z table. How do we use this? Our Z score was 0.4. So what we do is we look at 0.4. So we're going to look right here. Because it's 0.4, we're going to look at this row, right? So this row here, this column tells you, hey, 0.0, 0.1, 0.2, 0.3, tells you the tens place. This row tells you the number into hundredths place. So our number right now is 0.40. So the tens place was right here, so 0.4, and our hundredths place is 0, so we're going to be looking at this column. So where do they intersect? Right there at 0.1554. This is the probability of a score, a value lying between our 63 and 65. Okay, so let's go back over here. So this tells us 0.1554. And actually, I'm going to write this in a different color here. What this tells us is 0.1554. This is all right here, this shaded spot. So with this being 0.1554 and that shaded, we don't want that shaded. We want this shaded. But let me explain something to you. If everything under this curve is 1, well, this is the mean. This splits the whole curve. So if the whole thing is 1, what's half of 1? It's 0.5, right? So everything from here over is 0.5 all the way. And notice that we want this piece. We know this piece. So if we take all of over here, this 0.5 all in here, and we get rid of this, then what are we left with? We're left with our orange shaded region, which is what we want. So the math we're going to do behind this, we're going to say 0.5 minus our 0.1554, and that's going to give us 0.3446. This is our shaded region that we wanted. So what is the probability that a random selected student scored more than 65 on the exam? It is a 0.3446 chance that they did. Or you could say percentage to be 34.46% chance if you want to convert to percent. Let's move to the next one, and we'll keep seeing different types of things. So B. B says find the probability that a random selected student scored less than 85 on the exam. So let's visually draw that. So remember, our mean, our average is still 63. And we're trying to say out here at 85, we're trying to find all of this in here. Okay, our goal is to find all that shaded region. So first off, let's find how many standard deviations away this x value is. So z is x minus mu over the standard deviation. Our x value is the same. It's still 63. Oh, no, sorry. Our x value is different. It's 85. Our average, our mean is the same. It's 63. Divided by standard deviation is still 5. That gives you 4.4. So your z-score is 4.4. So what do? Now we go to our table. So let me erase what we've done before. Okay. Let's look at our table. So the value we're looking for now is 4.4. So we look here, this first column, remember it tells you your whole number and then your tens place. So let's keep going. So as you progress and we see, okay, 0.0, 0.1, 0.2, 0.3, we keep going. We see 1, we see 1.1, we keep going. Here's 2, 2.1, 2.2. Here's 3, 1, 2. What? 3.4? We got to go further. Well, what do you start noticing about these numbers down here? Look at these numbers. Look how they don't change as much. All in here, man, they change. Okay, right here, these back two numbers change. Right, and all of a sudden, the whole thing changes. But look at here. The same, the same, the same, the same. Okay. The same here, the same there, the same to here, same to there. What do you think is going to keep happening? We're getting really, really far out there, right? Because past 3 standard deviations away is only 0.3% of the data split in half, which is 0.15% of the data. And that's not a whole lot. So there's not going to be a lot of change, which means when we have a z value bigger than 3.4, we are going to assume and believe that our percentage, our probability, sorry, not percentage, our probability is going to be 0.5 because that's the number that we are approaching very, very close to. So we don't even need to look at anything. Once it's bigger than 3.4, boom, I should say 3.49. So bigger, so basically 3.5 or larger. We're going to say, oh, hey, you know what? That probability is 0.5. So what does that mean? That means that right here, this to us is 0.5. That's what we're going to assume right now. Okay. Well, look at here. Isn't from here halfway over also 0.5? Okay, great. So what does that mean? That means 0.5 last time I checked plus 0.5 is 1. So what's our probability? 1. It is 100% chance that a selective student will score less than an 85 on the exam. Okay, that's the probability of this happening. All right, moving on. We have C, part C says, find the 90th percentile. So when we say find the 90th percentile, that means we're going to find at 90% and lower. Okay, so here's what the visual looks like. So we're here 63 right here. We know 90% is over here somewhere. And how do we know that? Because if and I should start shading. If this is 50%, then we need to try to figure out this other piece. And this other piece right here is 40%, right? So how do we find what this value is? Because we don't know what the score is right here. We don't know this. So that's what we're trying to find. So first off, what we need to do is we're going to go to our Z table. But why do we need to go to our Z table? Because if this orange shader region is 50%, but we said 90th percentile, that means that we are looking for 40% from here to our X value. Well, we don't have a Z value, so we need to identify what the Z value is. Once we have the Z value, because remember, let me go back to here. Z equals X minus mu over the standard deviation. If I have 3 of those variables, I can find the 4th one. Right now, we have mu, standard deviation. We do not have X, and we do not have Z. X is what we're really ultimately looking for, but because we have the percentages, then we can find Z, because that's what Z helps you find. So what we need to find now is 40%, the 40th percent. So we're looking in here for the number closest to 40%, which looks like right about here. I should get a highlighter here. Right there. That's the value we're looking for. If we go below it, it's too far below. If we go above it, it's too far above. So which is closer? The 0.3997. And we are estimating a little bit, yes. So we're going to look at the number 1.2. And then we have 0.08. So we are at 1.28. That is our Z value to find that 40% or that 0.4000. So we know that our Z value, the 1.28 gives us the 0.3907 or 97, sorry, 97. So now Z equals, we know our Z value, which is 1.28. Our X value, we still don't know. Our mu is still 63 and our standard deviation is still 5. So if we multiply both sides by 5 and then add 63, we get X equal to 69.4. This is where the 90th percentile lies. So 69.4 is our answer right here. So 69.4 is the number we're looking for. Anyone who scores above a 69.4, there's only 10% of the people that scored above a 69.4 on the exam. Let's try another one. Let's try, let me do this here. Find the 70th percentile. What I want you to do here is I'm actually going to pause this, stop the video. I want you to find the 70th percentile, see if you can do it, and then when you're done, come back and check your work. All right, so how'd you do? So you should have gotten 65.6. So let's just walk you through it really quickly. So we know that we have 50% of the data lie here. We're looking for 70, so we know that we have 20. So now we're going to go to our Z table and look for the closest value to 0.20. This is 0.0015 away. This is too large. That's 0.0019 away. So we're going to choose this. Here we have 0.52. So there's our Z value. So we go back here. Our Z value is 0.52, right? That's what gives us the closest number to 0.20, 20%. So 0.52, our mean is still 63, our standard deviation is still 5. We multiply both sides by 5. Then you're going to add 63 to both sides, right? Because you got to get rid of this. And you get X is 65.6. So 65.6, there's 70% of the students that scored below a 65.6. which means that there's only 30% of the students that scored above 65.6. Okay, let me erase this here so we can use it again. And now we're going to go to our last example of this section and chapter. So go ahead and you go ahead and pause it, write this down, and then I'm just going to talk about it. So by now you've written it down because I'm going to start talking about it. So a personal computer is used for office, work at home, research, communication, personal finances, education, entertainment, social networking, and a myriad of other things. Suppose that the average number of hours a household personal computer is used for entertainment is 2 hours per day. Assume the times for entertainment are normally distributed and the standard deviation for the times is half an hour. So before we do anything, let's just identify what it just told us. First thing, it just told us that our average is 2 hours per day, right? It says that entertainment, see the, where does it go? The average number of hours is 2 hours per day. So we know that mu is 2 hours. Then it says the standard deviation is half an hour. And so because it's all in terms of hours, standard deviation is 0.5. That's what we get from that top. Now it says, find the probability, here's what A says, that a household personal computer is used for entertainment between 1.8 and 2.75 hours per day. So here's what it looks like graphically, more visually. So we know the average is 2. We have 1.8, and we have 2.75. We are looking for this piece in here. Okay, that's what we're looking for. But let's find it separately. So let's first find this piece. We're going to call 1.8, just for our purposes, our first z-score. It doesn't matter what order you put them in, so we're going to say our first z-score. So our first z-score says that we're going to have our first x value minus mu over standard deviation. It's 1.8 minus 2 over 0.5. This gives us negative 0.4. Okay, so what percentage does this give us? Let's go back to our table. I don't see any negatives here. What do? You treat it like it's positive because this talks about your z value is the probability between that middle and your x value. Okay, so we're going to treat all of your z values as positives. So we need 0.40 is what we're looking for. So here's 0.4 and 0, and we are right here. So 0.1554. So this value right here is 0.1554. Okay, now let's find our second z-score. We'll use a different color here. Okay, this is our second z value. Again, it doesn't matter if she uses first or second. I just do it so we can talk about it. So I'm going to use my second x value, same average, standard deviation. So I'm 2.75 now, minus 2 divided by 0.5. This gives us a positive 1.5. Notice it should be positive. It's to the right of the mean. So now we're going to go to our table and go to 1.5. So here is 1.5, and it's just 0. So we're just going to go right here to 0.4332. So this little purple spot here is 0.4332. We want everything between them. What's the probability of everything lying between? So how do we figure that out? right? You're going to take and say that I need to know all of this here to here. What is the probability from there to there? So what do? We add the two numbers together. So 0.1554 plus 0.4332 equal to, we add those together, punch them in our calculator, and we get 0.5886. This is the probability that the household computer is used for, or sorry, between 1.8 and 2.75 hours per day. Okay, we're going to do one more here. This is going to be a little bit different. So it says find the maximum number of hours per day that the bottom quartile of households uses a computer for entertainment. What are the bottom quartile? Well, you're splitting things in fours, which means that if you take 100% of something and split it into the bottom fourth, that tells you that you are finding the 25th percentile. Right? How do we know that? Because if 25% lies here, then we're looking at the 75%, which is also over here, right? Because 75% lies there. So what does that leave us? Well, if we know, let me erase some of this. If we know that this is 0.25, then we know that this piece over here is also 0.25. So we need to go to our Z table to find out what Z is that gives us that 0.25. So we go here. 0.2, right? And then 0.05 is here. So what we're looking at is we're looking right here, the 0.0987. Oh, I'm sorry. I looked at the wrong thing. My fault. We're looking inside the body. The 0.25, we're looking in here. My fault. We're looking in here. Okay. So we look 0.24, 0.24, 0.25. So it's one of these right here. So we look and say, well, which one is closer to 0.25? This one right here is 0.0014 away. And the second one is 0.0017 away, which this is closer. So our value we're looking at is right here. Okay, so what is our Z value? Our Z value, we're looking at this, our Z value is 0.67. I apologize for hopefully not messing too many of you up on that little mishap that I have. So 0.67 is what we're looking at for our Z value. So go over here. So 0.67 is what gives us that 0.2486, really close to 0.25. Z is x minus mu over sigma. So 0.67, we do not know our x value. Our average is still up here, right? We found out was 2, and our standard deviation is 0.5. That doesn't change. So we go minus 2 over 0.5. And when you solve for x, you get 1.665. But you might want to round up, but you don't round up because now you're skipping some. So what you're going to do is you round down. So x is actually 1.66, and then it's hours. So here is our answer. So remember, we have to round down here. Okay, and that concludes our chapter 6 of the normal distribution.